Well, good morning, everyone. Welcome to our second Q&A session. Thank you all for joining us this morning. My name is André Tétreault. I'm Director of Test and Diagnostics here at VibroSystM. I am joined this morning by Mr.Paul Amelinckx. Paul is one of our analysts at the Test and Diagnostics division. So good morning, Paul.
Thank you, André. Good morning. Hello, everyone. For our friends in Latin America and Brazil, please feel free to submit your questions in Spanish or Portuguese. We will be glad to answer them as well. Para nuestros amigos en la América Latina y Brasil, ustedes también pueden formular sus preguntas en español o portugués, las que responderemos con mucho gusto.
So, our objective today, of course, is to answer as many questions as possible. We had quite a few questions during our last Q&A session. And some of them we simply didn't have the time to answer all of them. So we're going to start this morning with those questions, make sure that questions that are submitted are actually answered. And then we'll follow up with new questions that will come up during the Q&A session. And if we have time, we'll cover a case study, one of the many case studies that I use during my training courses. And I think you'll find it interesting. Now, remember, if you want to submit questions, you have to log on to your YouTube account. So if you want the questions to show up on the right in the chat section on the right, you have to log on with your YouTube account. One of the first questions that was asked during the last Q&A session is, well, in fact, it wasn't a question, it was actually a comment, and it was from a Mr. Solis. And he mentioned that the equipment that he has from VibroSystM is very good and it's easy to use, but his only problem was data interpretation. And well, I can understand that data analysis is difficult. That's why we provide a list of services, what we call our result interpretation services, where we look at the data and we crunch it all and provide reports. We also have diagnostic training courses that we provide all over the world on hydro, on turbo, and even in the mining industry. Obviously, the Q&A sessions that we're providing now has that goal as well, is to provide as much information, as much expertise as possible, so people can gain more and more knowledge on the subjects. And finally, the Zoom Watch platform that we provide to our customers is a step further in trying to get as much information as possible to customers, especially utilities who don't necessarily have the resources, they don't necessarily have the expertise, and they would still like to get as much return on their investment as possible. So that platform is for that purpose. But yeah, I understand the difficulty of using the data and trying to do some diagnostics to help you along with the management of your units. We had a second question from a Mr. Kanan, who mentioned, is it necessary to monitor bearing acceleration and shaft displacement vibration in a hydro generator? And which one you recommend if we need to monitor any one of them? Well, my opinion, the most important one, they're both important, but the most important one would be shaft displacement for multiple reasons. First of all, if you want to alarm on the shaft displacement severity, well, you need shaft displacement probes. If you want to balance the rotor, you need shaft displacement probes to do that. So any kind of analysis using amplitude, frequency, and phase for the shaft, the better choice is displacement. Now, if you do have budget for accelerometers on the housing of the bearings, that's fine. You may find some very interesting information from those sensors, frequency information. For example, on the turbine, you'll see frequency coming from the turbine blades. And in some cases, you will have some vibration of the shaft, which seems excessive. And in reality, it's a combination of the shaft displacement and the actual bearing movement on which the sensor support is installed. So both of them can be useful, but if you can only use one, my recommendation would be to use shaft displacement probes. We had a third question from Mr. Solis, and the question was in Spanish, so I'm going to ask Paul to take a shot at answering this question.
Yes. ¿Qué opina del mantenimiento predictivo por confiabilidad y su aplicación con VibroSystM? En realidad, señor Solís, el sistema Zoom es la herramienta perfecta para implementar estrategias de mantenimiento predictivo o basado en condiciones. Los datos proporcionados pueden permitir fácilmente a los usuarios de las centrales identificar tendencias en el comportamiento de las unidades, diagnosticar las fuentes de problemas de lenta evolución, identificar los inicios de mecanismos de falla y planificar las paradas de máquina en consecuencia. Los datos proporcionados por el sistema Zoom también pueden permitir a las centrales determinar si los trabajos realizados durante dichas paradas fueron exitosos o no. Además, en las centrales eléctricas donde hay múltiples unidades, el sistema Zoom puede permitir a las empresas de servicios públicos determinar qué activos requieren una atención más urgente. Esta información crítica ayuda a preparar un plan de mantenimiento basado en el estado de los activos en lugar de un programa tradicional de mantenimiento basado en el tiempo.
So, in English, the question was, what do you think about predictive maintenance for operational reliability in its application with VibroSystM? Well, in our opinion, the Zoom system is the perfect tool to implement predictive or condition-based maintenance strategies. The data provided easily allows utilities to trend unit behavior, diagnose the source of any developing issues, allowing you to plan outages, not only the time frame for the outage, but the date, to be able also to mobilize resources, make sure you have all the parts, make sure you know exactly what needs to be done. And if you do have data, live data from your unit for a certain period of time, you're able to assess what the situation is. How severe is it? Do you need to take action? And if you do, you can better prepare to make that outage much more efficient, not only in its duration, but also when you put the unit back online, you can see the effects of your actions and be satisfied with the results. We had a question from Techmantic and Vision, and the question was, our bearing clearance is 450 microns, but the vibration actually goes up to 550 microns in certain conditions, if I remember correctly. They found no abrasion on the pads, there's no temperature rise. What could be the reason? They mentioned that, again, the clearance is 450 microns, but the vibration is at the turbine is 100 microns peak to peak, which is excellent. But the lower guide bearing, just below the rotor, the vibration values are actually 450 microns peak to peak. And above the rotor, they're 550 microns peak to peak. Of course, I assume these readings are taken with shaft displacement probes, not accelerometers. When you have higher results at the shaft, higher than the actual bearing clearance, there's a few possibilities that come to mind. First and foremost, when you mention that the clearance is 450, is that the specified clearance, or is it actually what was measured? Because obviously during operation, if you have excessive vibration, that clearance will actually increase. So the first thing to check is to make sure that the clearance is still 450 microns peak to peak. In some cases also, when people use inductive probes, the calibration is incorrect, and you will measure more or less vibration than is actually the case. So the second thing would be to check and make sure that if you do have inductive probes, that the calibration is correct. The third and foremost is, as I mentioned previously, the question about shaft displacement versus accelerometers. You can have a situation, and I've seen it a few times in the past, where the bearing housing vibration is quite high as well. Remember, the shaft displacement probes are installed on the bearing housing, and if the bearing housing moves as well, you will have a combination of the shaft moving inside the clearance and the actual bearing moving. And those two can add up to a value that's actually higher than what the clearance is. So First and foremost, check what the gap is, what the clearance is. Second, check the calibration of your sensor. And then third, you might want to think to put some accelerometers on the bearing housing and see if that actually is contributing to the vibration. In this case also, the vibration was very high on top of the rotor. So you might want to install accelerometers on the upper bracket, especially if the upper bracket is only fastened to the frame. It's not fastened to the concrete housing of the unit. You might have a situation where there's tremendous amount of vibration there. We had another question from Mr. Dixit. What are the benefits of using AGMS in old units? Well, they can be very helpful. Obviously, if you have a brand new unit, you want to get a system in there to make sure that the unit that was delivered meets, the minimum specifications. But for older units where the warranty is no longer an issue, again, it can allow you to help you plan your outages. It will help you determine what the situation is if you have an evolving problem, being able to intervene before it's a major failure. If you have a stator bar vibration, well, you might want to fix that before it actually fails, and then you have a phase to ground fault. And not only do you lose your winding, but you lose the core as well. So all of these situations are subject to monitoring to help you understand what the unit is doing and help you prevent major failures. We had an example in a power station in Canada where they went through a major refurbishment for their turbines. They went from propellers to Kaplan turbines, and shortly thereafter, one unit slowly saw the shaft vibration increase above the rotor. So they assumed that they had an issue with the rotor or the stator, but their air gap system showed that they had no issues whatsoever. So, to make a long story short, they investigated and found that one of the blades of the turbine was actually hanging off because a coupling stud had broken. So it was well, it wasn't completely off, but it was leaning towards one side and was completely unbalancing the unit. And that's why the vibration at the upper guide bearing was showing up as higher because of the imbalance. Now, the OEM had suggested they stop all 16 units until they could resolve the issue. Utility, that was a totally unacceptable proposal. What they said is they had monitoring systems on all the units. They had observed the issue. They know exactly what the profile of the problem is, and they were going to monitor their units. And if any of the other units had the same profile, well, they knew what to do. So they ran the other 15 units, and when the OEM had found a solution, the solution was implemented on all units, and they saved quite a lot of money. Another question, end winding vibration. Does your group recommend maximum vibration levels in order to avoid failures? Yes, we do. Unfortunately, there are no international standards for end winding vibration. IEEE came out with a document on end winding vibration, but they had numbers that were simply suggestions. They were not actual tolerances. I also participated in a committee for IEC briefly, because during the meetings they mentioned that there would be no tolerances in the document. So I felt this is not necessary to continue to participate. So there are no international standards, but we've been monitoring end winding vibration on turbo generators, on sag mills, ball mills, on hydro generators for over 25 years. And we have our own values that we use to assess the severity, and quite a few customers use those same tolerances. The next question was submitted by Mr. Monroy, and it's in Spanish, so I will let Paul take care of this question.
Yes. The question is, ¿hay nuevos equipos portátiles para monitoreo y análisis de vibraciones en turbinas hidráulicas? Y la verdad es que nuestro equipo está diseñado para ser instalado permanentemente y creemos que el monitoreo estático, digamos temporal, no representa toda la historia de la unidad. El monitoreo continuo está viendo el comportamiento de la unidad en el tiempo y puede detectar cualquier cambio. Un equipo portátil puede fácilmente no registrar eventos importantes.
So in English, the question was, are there new portable equipment for monitoring and analysis of vibrations in hydraulic turbines, and specifically for the analysis of the vortex in Francis turbines? And the answer, quite simply, from our perspective, is that our equipment is designed to be permanently installed. In fact, we don't really believe in portable equipment taking just spot pictures of the behavior of the unit at any given time. We don't think that's the best philosophy or the best approach, best strategy to be able to trend the behavior and also understand the unit's behavior under all conditions. We believe that to do that, you need to have online permanent monitoring so that you can see, for example, hydro generators in the northern hemisphere. They quite often have very different behaviors depending whether it's summer or whether it's winter. Just the concrete of the dams will expand and contract, and it will change the behavior. And if you have a portable system and you take readings once a year in June, well, you'll never see that type of behavior. So we believe in online permanent installation, so we don't really sell portable equipment. We have a question from Mr. Dhirendra. It's, if turbine vibration increases on application of the field, what could be the probable cause? In this case, of course, a hydro generator. We have a case where this happens. The turbine vibration decreases on field application, and while the unit is producing power, the unit is okay. Well, it doesn't give me a lot of information. I have questions. If Mr. Dhirendra is online or would like to join us at some time, I would ask him if the vibration at the turbine decreases, what happens to the vibration at the other bearings? Does it also decrease? I mean, when you apply in the field, you expect to see the vibration decrease because the rotor and the stator become magnetically coupled, and that usually settles the unit down significantly. So if you have that situation where the overall vibration of the unit decreases, I would expect to see the vibration at the turbine decrease as well. And my other question was, well, what type of runner? Is it a Kaplan unit? Is it a Francis? Is it a Pelton? So if Mr. Dhirendra is online, if you could provide us a little more information, maybe we can add some information to my answer. And we also had a question from Mr. Gupta. And the question was, can one view results of PD in picocoulombs of generator if installed the PDA 200 diagnostic module that we provide? And the answer, quite simply, to that is no. The PDA 200 does not measure in current, it measures in voltage. So it will be able to display the quantity of pulses, the general location of the pulses, and the intensity in millivolts. It does not display or measure data, PD data, in picocoulombs. So, do we have any questions, Paul?
Yes, we have a question. Mr. Dhirendra just logged in and says upper guide bearing and lower guide bearing remains the same. I don't know if that clarifies your question back to him.
Okay, I would ask him what type of runner, and is this a vertical machine?
So we'll wait for Mr. Dhirendra answer.
Yeah.
We don't have another one, but we can maybe go to the questions from the last webinar.
Okay, we had a question during our webinar in regards to uneven air gap. During the 3-day webinar we held in May, there was a whole chapter on rotors and a whole chapter on stators, but there's also a chapter on transient conditions. And we had a whole section also on mechanical centers versus magnetic centers. And I went through the whole process of explaining how this issue of magnetic center versus mechanical center is often undetected. And the reason for that is that if you look only at the vibration panel, if you have excessive vibration at speed no load before excitation, which is quite often the case, when you apply the field, as I mentioned, it becomes magnetically coupled, and you should see the vibration decrease. But if the air gap is uneven, what happens is when you apply the field, the unit, the rotor, will tilt towards where the air gap is smallest prior to the excitation. And what happens there is that the coupling becomes so intense that the vibration decreases significantly. So if you're only looking at the peak vibration, you will see the vibration decrease significantly, leading you to believe that the unit is performing very well. There's not a whole lot of people that actually look at the gap between the shaft and the bearing. They will just look at the peak. And if you have an uneven gap, air gap, and you have this magnetic center issue, the unit is subjected to a much greater stress than what it's actually designed for. As the rotor rotates, you will see the poles, the pole attachments, the rotor rim, in fact the spider arms as well, are subjected to varying magnetic stress. As the components get to where the air gap is smaller, the magnetic flux intensity is much higher, and then as it rotates away, that magnetic field intensity decreases. So you introduce a varying magnetic flux intensity per rotation, which is a perfect way to create metal fatigue, make component fatigue. So you create this vibration that will eventually cause damage to the components of the rotor. What you also have is that the magnetic flux being stronger where the air gap is smallest, it also applies much higher stresses to the stator core than what it was designed for. The magnetic intensity is much higher. You will probably see more stress applied to the stator bars because the flux is higher, so you can expect to see higher stator bar vibration. You will see eventually overheating and all kinds of potential issues. And the question of the gentleman here was, well, would you correct an uneven air gap by balancing? And if yes, my question is, what electrical components might be highly stressed because of this exercise? Well, the answer to that is no. You do not correct an uneven gap by balancing, unless your uneven air gap is caused by excessive shaft displacement, whereas the rotor is moving around erratically around inside the stator, and it's causing an uneven air gap. If that's the case, you might want to try balancing the rotor. But if your air gap is uneven only in one direction, causing this mechanical and magnetic center issue, balancing will not fix the problem. Yes, Paul.
Yes, we have an answer back from Mr. Tétreault. I'm sorry if I'm not spelling your last name correctly. He says, yes, it's a vertical machine. It's a Francis turbine.
It's a Francis unit, and the turbine vibration decreases as they apply the field. If the others, are the vibration, I'm going to ask another question again, sorry, but are the vibration levels at the other guide bearings near the rotor, are they high or are they low?
We'll wait for his answer back.
Might be also interesting to find out when it decreases from what to what? Is it a significant decrease or just a slight decrease?
Yeah, we have another question from a gentleman or lady, I don't know, is Gigi Senei. Do you have condition monitoring training courses for hydro generators and WTGs online? WTGs. I don't know what it could be, but I would guess it's turbines, a turbo maybe, I don't know.
Of course, yes, we have, I've been giving training courses on hydro generators and turbo generators and sag mills for close to 20 years now. The courses are usually 3 days. Well, they are 3 days, but they turn into 5 days if the customer wants to have simultaneous translation, which I've done many times in South America and in Asia. So yes, we have comprehensive training courses. Again, we cover the types of monitoring that is in the market. We cover all the different terms that are used, you know, for rotor circularity, concentricity, nominal air gap. We go through how to analyze the performance of a rotor, how to analyze the performance of the stator. Again, we look at transient conditions, which can be very interesting. You look at startups, what happens to the unit when you increase the speed, what happens when you apply the field, what happens when you synchronize to the grid, and then you increase the load, what are the effects of elevated levels of temperature to the unit. Sometimes it's very dramatic. What happens if you operate the unit in a synchronous condense mode? What happens when the unit goes through the rough zone? Many hydro generators have rough zones. And my personal favorite, what happens when you perform a load rejection? So those are all covered. There's also an entire section on relative vibration, on absolute vibration, different terms used, the do's and don'ts of using different types of sensors, the many mistakes that are made using this type of equipment. It can also come with an exam if the utility wishes to have an assessment of how well the students performed. The training courses can be done through webinars, as we did in May, but historically most of the training courses were held at site. So I would travel to site and give the training course to the engineers on site.
And we have another question also from Mr. D'Andrea. Does VibroSystM has any monitoring system for pole-to-pole connection health?
We have a, well, yes, we have a temperature probe, the thermowatch rotor, that is an infrared probe that is used either to measure the pole face temperature, and in some cases where the units are operated, you know, with new turbine technology, they're able to get an extra, 4 or 5% power out of the amount of water, and that power is then transferred, of course, to the rotor and stator into electrical energy, and that usually increases the heat produced. And it can be very important to measure the pole face temperature, make sure that the heat that is present does not exceed the limits of the materials. For the interpole connections, well, that same sensor can be installed in such a way that it measures the temperature of the interconnections. We had a case in France where they did that. And this allows you to see if there's any overheating interconnections, telling you that you have some deterioration of the interconnection, especially the rigid ones. The rigid ones are more susceptible to cracks because of the expansion and contraction of the rotor when you cycle the unit, and the rotor poles will extend outwards, and you hope that it does so symmetrically, but that's not always the case. And if you have a rigid interconnection, it will suffer more stress and will be more susceptible to cracks. And if you have cracks, of course, same amount of current will flow through less and less material, causing it to overheat. So it's an exponential, it's a deteriorating evolution. The flexible ones can still have issues, but they are more suited for that type of condition. But we do see some flexible laminated interconnections that do fail. So yes, there is a sensor. To monitor that, I would have air gap sensors and the thermowatch rotor probe to see if the interpole connections that are hotter than the others are located in areas where the poles have an uneven expansion.
And we have a follow-up question from Mr. Durandra again. TGV vibration are high, 500 micron pp, peak to peak at mechanical spin. Comes down to 200 on application of field, other bearings remain the same.
Well, I would love to see more data on that unit. It is possible that when you apply the field, the axial position of the unit will change. In most cases, the rotors are installed slightly lower than the core, so that when you apply the field, the rotor is slightly lifted, giving the thrust guide bearing a break. Maybe the change in axial position of the whole unit has an impact on the effect of water in the turbine. But with little information, that would be my first guess. As I mentioned, if you had any changes in the vibration near the rotor, I would assume that the magnetic coupling is stabilizing the unit. But if that's not the case, it has to do with the water. I would assume that when you excite the unit will lift somewhat, and that will change the dynamics in the turbine, causing it to settle. But to be able to confirm that, we'd need a lot more data.
And we have a follow-up on the WTG. It's wind turbine generators.
Ah, wind turbines. Okay. Well, we have equipment that we feel would work for wind turbines, although I don't believe we have any systems installed. The issue is, I think I mentioned in the last Q&A session, I often have a question when I discuss with utility engineers and some OEMs when we talk about monitoring and the costs, and a lot of people will say, well, you know, this is all interesting equipment, it's all interesting technology, but our units are very small, you know, they're 10 megawatts or 5 megawatts, and it's difficult to justify spending that amount of money on these types of units. And my reaction is always, well, you know, if your unit goes down for 6 months and has a major failure, is that a problem for you? And they will say, well, yes, of course. I mean, the unit is a very important asset to our company. We can't afford to have the unit down for 6 months. So my reaction is always, well, why are we talking about megawatts? The issue is not megawatts. The issue is how important or how critical is that asset to you. But for windmills, if you look at a wind farm, there's quite a few units, and each of these units produce a small amount of power. So they don't generate a lot of money, and if one goes down, because the windmills, of course, if there's no wind, they're not working. If you have a windmill that goes down, it's not that much of an issue so far as we can tell to the utilities. But if we just look at the units per se, we do have equipment that could easily fit in those units and could provide, you know, critical information, air gap information, relative vibration information, absolute vibration information, displacement, temperature, flux. There's all kinds of information that we could retrieve. Probably the biggest challenge would be to get the information out of the windmill to a central location for data analysis. That would be probably the biggest challenge.
And André, we have a follow-up question on the vertical Francis unit. This question comes from Terry H.E.P.P. Maintenance GRP. It says the gaps are 450 micron peak to peak, adjusted in every manual maintenance. But also says, please comment on how to segregate effect of accelerometers reading to find actual shaft vibration.
Okay, what you do is of course, the accelerometers, well, in our case, the accelerometers are usually installed on the same bracket than the shaft displacement probe. So you're reading displacement off the shaft, and with the accelerometers, you will double integrate down into displacement. And of course, that creates a 180-degree shift, but you can adjust that. And then you can compare the results of both probes to see if they follow the same same phase or not. And from that, you can either add or subtract the total displacement between the shaft and the bearing in combination to see if the first of all, is the bearing housing vibrating a lot, and if so, is it working symmetrically with the shaft or not. We do that also for core and frame structural integrity. In some cases, you will monitor the acceleration of the core and you'll see a certain amount of vibration. And you look at the frame and you see similar amounts of vibration. Usually you see a little more. And but if you look at the phase, you find out that they're not necessarily working in unison. There's a phase, there's a time lapse difference between them, telling you that there's some stator core looseness. And if that is allowed to remain, you'll have some issues between the core and the key bars, and you might have some arcing between the core and the key bar, which of course is very damaging. That's high intensity discharges, and you can seriously damage the core if you allow that to go on. So a combination of two sensors on the bearing housing or on the stator core and frame allows you to see if they are working together or if there's some kind of looseness issue there.
We have another question from Dejan Gutta. I'm sorry if I'm not pronouncing it properly. Is partial discharge analyzer important for vibration monitoring?
Well, I know that some partial discharge vendors will tell you that they're able to measure vibration based on slot discharge. Well, that's a little misleading from my view because, as I've mentioned before, our objective as a monitoring system provider is to detect and prevent damage, not to observe it. We don't want to record the damage, we want to record the behavior and prevent it. If you're measuring slot discharge and you're deducing that there's vibration, in many cases, if you're at that point, it means that damage has already occurred. The objective from our point of view is to measure the vibration and be able to go in there and apply corrective measures to prevent the bars from vibrating, making them tighter in the slot so they don't vibrate, so that you never get to a point where you start seeing high PD values. So again, high PD values, I've heard this comment before. This is, well, we can see some slot discharge which is due to vibration, and that's true. But the slot discharge is there because there's damage now. It's probably been vibrating for some time, and now you're at a point where you can see the slot discharge caused by the damage to the insulation. You're losing contact between the insulation and the core, and it's starting to discharge. So we strongly believe that's a much better approach to detect vibration early on and fix it before you have damage to the insulation.
We don't have more questions for the moment. Maybe we can continue with the webinar answers.
Yep. We had one question where we were talking about, we were in the rotor section. Again, there's quite a few techniques we use to determine the integrity of the rotor. And one, of course, is to verify if there's any rim looseness, which is quite common. There's a few types that I won't necessarily go into here, but there's two types of rim looseness that we look at. And the question was, how can you determine a loose pole condition versus a loose rim condition? Well, that's fairly easy. If you have a loose pole, you will see varying, I guess, radial position for that pole depending on the operating condition. For example, if you excite the unit, or if you run the unit that's been no load, or if you increase the load, you will see that pole move, and in some cases you'll see the pole vibrate. Whereas if you have a loose rim, you will have a section, you will have a series of poles that will stick out under specific conditions. So it's fairly easy to see, and as I mentioned during the training courses, it's rare to see a pole really sticking out. It does happen. One famous case in China comes to mind. but it's rare to see a pole really sticking out. We had also a case on a sag mill in South America where 3 poles were replaced and they were wrongly installed, and you can see they were seriously sticking out as opposed to the others. But if you have a loose rim, again, you'll have varying results. For example, you have over time a rotor that becomes elliptical, and it just never goes back to its original round shape. That's an indication that you have a loose rim. The rim distorts and just stays distorted, and at some point you need to fix that because it causes all kinds of issues to the rotor, to the stator, and possibly increase 2x vibration on the shaft. So again, if you have a loose pole, you will see one pole having some varying results. If you have a loose rim, you'll see either a section of the rotor that will have some varying radial positions, and in some cases you'll see rotors that will adopt a non-circular shape. These are all indications that you have a loose rim. If we don't have any more questions, we can maybe run.
Well, we have. We just got another one.
Okay.
This is from Mark Bissonnet. On behalf of a client in Southeast Asia, can you integrate air gap, vibration, temperature, and PDA in the same system?
Well, we can integrate just about anything you can think of. In fact, our Zoom system is designed to be able to accept data from existing equipment. The Zoom system is designed to be able to integrate as much information as possible. In fact, when we go into contracts with customers with our Zoom Watch service, we insist on having as much information as possible based on the phenomena the customer wants us to monitor. And we insist on having data from their SCADA system or their PLCs to be integrated, because there's a lot of behavior that is either normal or abnormal depending on what the operating condition is. If the unit is very hot, some behavior is normal. If the unit is very hot, some behavior is not normal. And it's important to be able to control those parameters so that we can easily determine whether this is an issue or this is normal. So we need all that information. So if we can get access to flux, air gap, shaft vibration, core vibration, frame vibration, axial displacement, turbine runner clearance probes, accelerometers on the bearings, temperature probes, pole temperature, interconnection temperature, along with all the auxiliary information, megawatts, megavars, speed, temperature, voltage, rotor stator current, all this information, humidity, all this information can be the important piece of information that is necessary to make a correct determination whether there's an issue that needs to be dealt with or not.
We have another question from Mark Bissonnet. Second question, what is the benefit of using 4 air gap sensors instead of 1 sensor for the hydro generator monitoring?
Well, you know, we have our own tolerance, well, not tolerance, but specification where you know, we would like to have the air gap sensor give you the best possible coverage. And if you have a very big stator, I know cost is always an issue, so people say, well, we'll just use 4 and we'll be able to monitor. But if your unit has a diameter of 12 meters, I mean, you'll have large sections of the stator without any coverage. So 4 is for small units. We go up to 6, 8, and 12. In some cases, when the stators are very high, we will put sensors on the top and on the bottom. And in some cases, people will put a certain number of sensors at the top, and they'll put just 1 at the bottom for verticality and to look at the rotor shape, which is not a bad idea, but it won't tell you what the stator shape looks like at the bottom. So using 1 sensor will give you information on the rotor, but it's not going to give you information on the stator. So the more information you have, the better position you're in to make assessments. So again, depending on the size, we put as many sensors as we feel is necessary to be able to come up with a good assessment of not only the stator shape, but its performance as it's exposed to a tremendous amount of heat. There's quite a few stators that we've seen that look fine when they're cold, but when you heat them up, they have sole plate issues, they have core to frame looseness issues, and when you apply heat for an extended period of time, these anomalies show up. And remember that when the units are full load, hot, that's where you usually want the unit to be, because that's where you're making money. There's a lot of people who take measurements cold, physical measurement, which is fine. It gives you an idea what the shape is when the unit is stopped and cold. But that's not really what you want to know. You want to know what the unit looks like when it's operating. For example, are you interested in your car oil temperature when it's parked in front of your home? Not really. You'd like to see what the temperature of the oil is when you're on the highway, at 100 kilometers an hour. So our philosophy is the same. We want to see what the unit does when it's operating, so that we can make sure that the unit behaves correctly and is working correctly where it is usually operating in those specific conditions.
And we have another follow-up question for Mr. Durandra.
Yes.
What other data is required regarding this vertical Francis unit? We already have Zoom system installed. Can it help in identification of the root cause for high turbine guide bearing vibration at mechanical spin?
Well, there's quite a few possibilities. I mean, if it's, I find it very curious that the turbine is very high, but the others are low when they're running at speed no load. It's usually they're usually either all at the same amplitude, or the upper guide bearing, lower guide bearing should be higher. I would be interested to see the results at all the different operating conditions and see if we can pinpoint exactly what's going on. As I mentioned, the axial displacement might be an interesting thing to look at. Being able to look at the vibration of the turbine from the perspective of frequency. Is it basically at the fundamental frequency, or do we have a series of harmonics? Is it a question of the turbine needing balancing? My instinct is no, because when you operate, it's very low, so you probably don't want to mess with the balancing of the turbine. It might be interesting if you could get in contact with us and maybe we can have a discussion on what you have on, because I'm not aware of the project, so we could take a look at what equipment is installed and see how we could find out what the cause of this. I mean, if you're going to have a problem having the vibration high at speed no load and having it very low during operation, that's probably the best problem you can have, because in reality, when you're operating, there is no problem. But I am curious to see why the turbine has such high vibrations at speed no load, whereas the other bearings do not. That seems a little strange to me. So I guess I don't really have a complete answer for you, but if you can, or if you want, you could get in contact with us and we could look at maybe more information, especially since you have the Zoom system. We could take a look at a database and try to find out what exactly is going on.
And we have another, the last question is Kaiser Iqbal. What could be the possible reason for a vertical Kaplan machine having high vibration when operating at minimum load?
That's more common. Minimum load, well, if minimum load, does that mean close to zero when you synchronize, or is it because you're running at, let's say, 25% load? Remember that, like I said, most hydro generators have a rough zone, and that can be anywhere from 15% to 50% load. And when you go into that zone, the unit becomes unstable. And usually what happens is you will see either the unit will start skating, which is a subsynchronous frequency where the unit will have a high level of vibration at a frequency which is less than the actual rotating speed of the unit. We see that quite often. We call it skating. So it becomes erratic and it starts wobbling around, but at a slower speed than the actual rotating speed. You also have, in some cases, the opposite. When you go into the rough zone, you will see some supersynchronous frequencies show up, supersynchronous harmonics, where you will see the unit will actually spin on itself multiple times per rotation. So if let's say the fundamental is 3 hertz, you might see a 9 hertz or a 12 hertz frequency show up, which is predominant. So the unit is actually spinning on itself multiple times per rotation. We see that in some occasions, and those are all phenomena that can occur in the rough zone. Now, if you have a unit that has this problem at all loads, that means you need to fix the bearing. If the vibration is immediately after synchronized, so that you're synchronized to the grid but you're not actually producing any power, that could be an indication of either a out of round stator, or it could be also a combination of rotor and stator. And if you increase the load and it settles, which is one of the reasons why we look at the stator expansion as well, some stators, when they expand, actually improve, which is good news. So that when you operate at higher loads, the heat will in fact fix the shape of the stator, and the unit will quiet down, the vibration will go down.
And we have greetings from Jonathan Hill. This has been some great information. Thanks for hosting, André. John from SC. And that will be it. There is one more question from Mr. Dhirendra to have our email. I would say, Mr. Dhirendra, if you could send us your email on the comments after this session, we will keep in contact with you about this issue you have over there. So now we can go up to
we can run the case study?
Yeah, absolutely.
Okay, so I'll let you start it up.
Yep, you have the control.
We're on? Okay. Now, this case study is, as I mentioned, when I give training courses, I have like 15 case studies that I can cover during a training course, depending on how much time we have. And these case studies are not simulations, they're not hypothetical. They're all actual cases that we've worked on. And this particular case, I was on site a few times. And this was a new power station in Brazil. It was the first power station in Brazil with horizontal units. Okay. Let's take the mouse here.
Yep.
Okay. As you can see, it's a horizontal unit. It's a fairly small unit, and it's very slow speed. And in this case, we installed 4 air gap sensors at 90-degree intervals, but with a slight offset of 45 degrees, which is what we usually do for horizontal units to get better coverage. They also had some shaft vibration probes and some temperature probes and some pressure probes. Now, they had 5 units, and unfortunately, the engineer who was was responsible for making sure that the units were satisfactory to existing tolerances. The engineer complained to his utility. He said, "Well, we don't have any monitoring. How are we supposed to verify if the units are in good shape if we don't have any data?" And he was able to convince them to buy into a monitoring system. But by the time they issued the PO, by the time we manufactured the equipment, have it shipped down to Brazil, the 2 units had already been commissioned, units 1 and 2. So when I went to site, I installed the system on unit 3, 4, and 5. And unfortunately, at some point, we got a phone call from the utility saying that unit 2 had rubbed. There was a rotor stator rub causing some serious damage, and to make sure that that didn't happen a second time, they wanted us to go down and make sure we install the system on the other two units. So I went down, installed the units, the system on units 1 and 2, and I decided to run a series of tests on all 5 units because I had a training course to give, and students are always more interested in data from their own units. I mean, it's looking at units from China or Congo or United States. It's all interesting, but it's always more interesting to take a look at your own units. And what I decided to do was take tests on all 5 units, and what we did is we ran the unit from speed no load up to 42 megawatts, and we looked at the results. So we did unit number 1, it was fine. We looked at number 2, which had failed, it was fine. So they had mixed feelings because they were happy that they didn't find anything wrong, but at the same time we didn't find any evidence that would tell us what happened. So we moved on to unit number 3, it was fine. And then when we got to unit number 4, we found something peculiar, and I just want to show you this briefly. I won't go into detail. During the training course we take at least an hour to look at the results, and I ask the students to try to tell me what's going on. There's a common rule that we have air gap analysis from XY graphs like this one, and it's that the air gap traces, okay, we have 4 sensors looking at the profile of the rotor for 1 rotation only. So this is 1 rotation. And the basic rule is that all the traces should be parallel, okay? So if you look at those results, they are somewhat parallel. Not exactly. If you have a trained eye, you'll see a difference. But this is the unit that's been no load. Basically, the traces were parallel. This is at 42 megawatts. I think anybody can see there's definitely an issue here. Okay. This sensor is not seeing the same profile in this location only than the other sensors. If you look at this section, they are all parallel, but this section is not. Okay. So what we were able to determine is that this unit had a rim that is not properly supported, and as we increased the load, the rim was actually slowly being pulled off of the spider. Okay, so we were able to prevent this from hitting the stator, and at the same time we were able to confidently assume that this is what happened on unit number 2. This section actually came off and hit the stator core. You can see how bad this section is. Remember, this is the same reading, okay, but this sensor was seeing a much greater anomaly than the other sensors. If we look at the polar graph, we can see this section here. Okay, this is at speed no load, and this is at 42 megawatts, and you can see how increasing the load was actually pulling this part off. Okay, so the OEM was able to come in and do some percussion tests on the rotor rim bolts and found that the rotor rim bolts on this unit actually broke when they tested them. So they replaced all the rim bolts with better quality bolts on all the units, and they never had a problem afterwards. Okay, so this is one of the case studies that we use during our training courses, and we have quite a lot of them. And I think they enjoy very much. I asked them to, form teams and use the knowledge that was given during the training course so that they can try their own expertise. So we're at the end of the Q&A. Thank you all for listening this morning. I hope you found it interesting. If you'd like to have access to more technical content as we covered today, don't forget to subscribe to our YouTube channel. Also, ring the bell if you wish to receive notifications of new content on the channel. Please feel free to write your comments or questions at the bottom of the page. Even after the session is over, we'll take a note of them, and we'll make sure, as we did today, that we answer all of those questions at our next Q&A session. Remember, the videos will remain permanently on our YouTube channel, so you can get access and listen to them at your convenience at any time in the future. So thank you all. It was nice to see you again, and hope to talk to you soon. Thank you.
Thank you very much. Hasta la próxima.